Yes, please.
Okay, so we're going to talk about torsion, possible torsion, infinite torsion subgroups and cat zero groups. So let's just get the setting. With X, proper cat zero, and G acting on X geometric. So proper just means that closed balls are compact, and a geometric action is a co-compact, properly discontinuous action by isometries. And the open question, this should be thought of as a therapy session, dealing with my problems. Can G have an infinite torsion subgroup? And the answer currently is unknown. So
Expected answer?
expected answer is no. The expected answer is no. There is a bound on the size of a finite subgroup in a cat zero group. So any such thing would have to be something like a Burnside group. It would have to at least contain an infinite, finitely generated torsion group. Right? Might not itself have to be finitely generated, but it would contain one. So there are partial answers in other settings. No. If G, or if X is acute. And in fact, there's a stronger result. If any torsion group that acts on a proper cat zero cube complex has to fix a point. So this is due to Sageev and other people, probably Wise, Caprace, and there's other people, right? They just, well, I guess just Wise and Sageev shows that it either fixes a point or it fixes a point in the boundary of the group, and then from there you can get it using results of other people. Cologne and Giardelli have an example of a I'll have to spell these because I'm sure I mispronounced them. You generated infinite torsion acting properly. On infinite dimension. Since it's infinite dimensional, it will be proper. But anyway,
So if you say infinite dimension, it means
there's no bound on the dimension of the cubes. Yeah. Okay, so yeah, wait, that doesn't work very well, does it? All the way down. Turns off as soon as it goes below a certain level. Great. Okay, so well, let's draw our picture. Maybe if you lift that up and Lift him back a bit. No? Ah,
Yes.
there. Okay, but I need a footstool to draw now, though.
I've seen a number. So for the first half, you can write with the blackboard down.
Ah. Yes, that's.
The detectors are there.
Mm.
So maybe you simply need to raise this high enough. You see?
Yeah, well, I'll draw with it low and push it up when I get that far.
Yeah, that's the idea.
Okay, maybe draw on my knees. So in X, let's draw our classic picture. Just, I know you've all seen this before, but. So we take a geodesic triangle in X. And there is in Euclidean 2 space the corresponding triangle called the Euclidean comparison triangle, which has the properties that the side lengths are the same. Right? And now the cat zero condition is for any 2 points I choose on the triangle, I can choose the corresponding points on the Euclidean triangle. This would be, say, P, Q, P hat, Q hat, and the cat zero condition says that the distance from P to Q is less than or equal to the distance from, or other way around. Okay, so that's the standard definition of a cat zero space, is that whenever I have a geodesic triangle and I look at the comparison triangle in the Euclidean plane, I get that inequality on the things. Now we look at the angle here in Euclidean space. It is.
You're right. Think of a tray.
Ah! Yes, it's the other way around. Okay, we
Yeah,
have
you were right first time.
I was right the first time and I just didn't trust myself. Okay, anyway. Now, theta, which of course is equal to the angle at A hat of B hat comma C hat, that is called the Euclidean comparison angle for the triangle in Euclidean space. And this little inequality here implies that if we take the Euclidean comparison angle at P hat comma Q hat, that's less than or equal to, well, theta, right? Because the distance gets smaller. Well, sorry, that's not what I want to say. I want those things to go away, and I want that to have a bar. There, that's what I wanted to say. Okay. So as we move closer, the comparison angle decreases, and now we just define the angle to be equal to the limit as a E goes to A, and P goes to, A, and Q goes to A. Okay, and that will always be, that limit will always exist because of this monotonicity condition that we're seeing here, right? We get monotonicity in the Euclidean comparison angles. So that always exists, and it is in fact less than Euclidean comparison angle. And in fact, that can be used as an alternate definition of cat zero, provided you can say what the angle is really supposed to be. You define it, I think, as a limb sup of the comparison angles. So it always exists. Now I think I push up, right? Let's see. There, I can probably draw. Okay. Okay, so what's the boundary? Equal to the collection of GDs. Unit speed, GDs rings, modulo equivalence, where we say alpha is equivalent to beta if the distance from alpha t beta t is bounded. So that's the definition of. Okay, so what does a neighborhood of a point in the boundary look like? So we take, we fix a base point. And we look at all the rays from the base point. And of course, every ray in here is represented by a ray in there, just by a fairly easy connecting the dots argument. And now we look at a neighborhood, U, R, and epsilon. So for R, a ray from x0, or a ray from x0, we look at that neighborhood and what does it look like? Well, here's x0, here's the ray R. We go out distance n. We take an epsilon ball around that guy. Right. Best looking epsilon ball. And a point is in this neighborhood exactly when the GDs at connecting it hits that epsilon ball. Well, we can change it slightly just to say the distance from S of t, or S of n, R of n, is less than epsilon. P, he can be either in the boundary or in the interior. This gives us a neighborhood of the so that's G to P units. So this topologizes the boundary, and in fact, this gives us a compactification of the cat zero space. So the compactification points of the rays and the boundary will be compact metrizable. So this thing is compact, metrizable, and finite dimensional. Which is strange because X most definitely does not have to be finite dimensional for silly reasons, but nonetheless. Okay. What?
The space is proper, but will not be finite dimensional.
Yeah, you can.
So what do you mean by finite dimensional in?
What do you mean by
unbounded
dimension?
Just take the topological dimension. It's all going to be the same. There's nothing that's going to be difficult, right? So, give me your favorite easy cat zero group, right? The torus, the fundamental group of the torus. Okay, so I take a torus, it's just a square, and I take a small 3 cube and I just glue it onto one side of the thing, right? And then I take an even smaller 4 cube and I glue it to the 3 cube as a face, and I continue that process forever, and I throw a point on top of it to compactify the whole mess, and that's an infinite dimensional cat zero space that's the torus acts on properly, discontinuously, and co-compactly. Right? There are silly reasons why X can be infinite dimensional. There are ways of probably avoiding that, but it isn't clear. Right? Anyway. Right, you can take a minimal convex subset in it, and in that case, all the bad stuff will get thrown away, but it isn't clear you can always get rid of the infinite dimensional stuff doing that, because there are examples where you have things that should be 2-dimensional that are actually 3-dimensional when you insist that they be cat zero. Okay. Now, so that gives us a topology on the boundary, but there's a different topology on the boundary that's also useful, and we need to look at both of them together. And in fact, there's a metric on the boundary that's going to be particularly useful. Okay, so we define the angle between two boundary points in the following way. Once again, we're thinking of them as GDZ rays emanating from a single base point, x0. Okay, so now we take the limit going the other direction, right? We take the comparison angle limit as the rays are going out to infinity. So here's a picture. Right. And we take those Euclidean comparison angles. Those are increasing, so this limit exists. It also, it turns out, at least in this situation, it's the supremum of, this is due to Bryson and Hefflinger, I imagine. Although it could be Ballman as well, it's hard to say. Anyway, so it's actually recognized. And in fact, I should say max. It's not just the supremum. The supremum is fairly obvious, but it is the max. Okay, so this gives a metric. Gives a metric. On the boundary X. Not the same one. This is going to be finer. In general, it will be finer than the original metric, the original topology that we have defined above. And now we take the path metric. This is the Tits metric. And it's equal to the path metric. From the angle. The angle metric. So associated to the angle metric, there's a path metric, right? The length of the path is gotten just in the way the length of the path. It's always gotten in a metric space just by partitioning and measuring distances and taking supremums. And of course, for that reason, right, the angle metric is always less than or equal to the Tits metric, but of course, the angle metric is always less than or equal to pi because it's an angle. Right? So it can't be bigger than that. If the angle between alpha and beta is less than pi, however, then the angle metric alpha beta equal to Tits metric from alpha beta. Right? So when you actually get an angle that's less than pi, those two things will coincide, and that's due to Bruce Kleiman. At least that's what I'm guessing. Okay, yeah. Now there's an obvious map. Okay, so T sub x is equal to the boundary of x with the Tits metric. Okay, and they are really the same space, right? So there's obvious maps. You have boundary x. Well, this is really the identity. And this is continuous, but the other way around is not. And this is only lower semi-continuous, which, if you remember, and even if you don't, if you have A sub n going to A and B sub n going to B, this is in the boundary of x, then you get the following inequality in the limits. It's Tits distance from A sub n to B sub n, and then we use lim inf there is greater than or equal to the Tits distance A to B, and oftentimes you will see a big drop there from the limit to the all right. Okay. Now, or let's say we have H acting on X. Once again, he's still properly at 0. We can talk about the limit set of H. This is the limit points of the orbit. Okay, take any point in the space, act on it by H, and look at the limit points. In the boundary, there may be none, depending on what there is, but this is the limit set. It's a closed subset of the boundary. So why are we talking about limit sets? Because that's where the first actual result we're going to see. Okay. So let's take a limit point of our subgroup H. We say alpha is conical if, and so this is a definition from Kleinian groups, so if you know anything about Kleinian groups, you already know what the answer is going to be. If for some, well, we might as well choose the base point A. the neighborhood about alpha radius n intersecting the orbit is unbounded. It's arbitrarily far from zero. So the picture, of course, looks like this. We have our ray alpha. We have a little tubular neighborhood about it. Right? And you have a bunch of points. In an orbit that go up towards the end of it. Okay. Now, an actual theorem.
So what is the topology? I mean, so that's the topology of which gives sort of a modification for. What's the neighborhood of alpha then?
Okay, this is just a subset of, this is in X. X is a cat zero space. We have a prescribed metric, so this is just a neighborhood in X. There's nothing difficult here.
It's a neighborhood of just one ray.
Just I pick a particular ray, alpha, and I take a neighborhood of it, n,
So
and
alpha is not a point in the boundary.
alpha is a point in the boundary, but a point in the boundary is a geodesic ray. So I choose a representative, any representative I want, it's not going to matter.
But for instance, say if you're in Z2 and your group is I mean, you might have a particular neighborhood of one ray where this happens, and another one that's not intersecting.
Yeah, but
Parallel.
n can be chosen to be however big I want.
So for some x naught and for
Yeah,
some
some
y.
n. Yeah, we should have put that there. Yeah. So n can be chosen, we don't care how big n is. Right? It can be as large as you want, but we just want that to be unbounded. And so that's independent of the choice of alpha and n, or I mean and x zero. Right? For any other choice of alpha.
Oh, you mean it's a tube of radius n around alpha?
Yeah.
It's not a cone. They're different.
It is a cone. If you look at hyperbolic 3 space, let's draw a picture. I'll draw the two-dimensional picture.
Okay, there are different notions of conic limits.
And that is most definitely a neighborhood of this ray. And if you think of the 3-dimensional picture, that's where the word conical came from, because this is what a neighborhood of a ray looks like if you take the upper half space model and you take a vertical ray, like you probably want to. Right? Then it's exactly a cone. I mean, it's not my choice of notation, I inherited it. Anyway. So,
You draw an orbit that fills in the tube, right?
it's
But it's not required. It's
just
required
unbounded.
unbounded, right?
Yeah. It's just unbounded. We don't require it. Okay, so now we actually get a theorem, which is good because it's been a while. Haven't gotten anything yet. Theorem. If H acts on X by isometries, and H has a conical limit point, then there is no bound. On the orders of elements So that doesn't say that H has to have an infinite order element, but it does say that H has elements of arbitrarily high order. So it could still be a torsion group, but it's got some pretty big torsion stuff in it. Okay, so now, since it's a conical limit point,
So the action of H on X is not assumed to be geometric, it's just.
no, it's not assumed, it's
It's just
any action, yeah, it
Just
doesn't
by
have to be
isometries,
discrete,
yeah.
doesn't have to be discrete, does have to be by isometries. Doesn't have to be discrete, doesn't have to be proper, doesn't have to be compact, doesn't have to be anything.
Semi-simple.
Yeah, there's no requirements whatsoever, yeah, this is entirely. Oh, yeah, this is working out okay, I guess, just have to get used to it. Okay, so the point is, we choose, well, I'm just going to show you this because this has interesting consequences. So there exists increasing sequence 0 to infinity with p sub n going to infinity, of course, such that h sub n of alpha p sub n is contained inside a set we're going to call C, which is the ball about our point x0 up there of radius n, and we'll call it the closed ball. Okay, so the point is, you can think of, let's pull this down. These are, of course, in here, well, inverse there. No. H sub n inverse of alpha with p sub n. No. Sorry, I'm drawing the wrong picture. That is alpha with p sub n, and this is h sub n inverse of x0 is what that guy is. Okay, that's better. Lights, please. There we go. Okay. So if you think about how we're choosing them, these are how we're choosing them, right? Those things are within n, so when I hit it with h, it comes back inside this. And now we just reparameterize a bunch of the geodesics. So let alpha sub n, it's a unit speed geodesic, but I'm going to change the parameter. Geodesic. And the way I define it is just, so alpha sub n of t is going to be h sub n of alpha of t plus p sub n. So it's really just alpha hit by h sub n, but I'm reparameterizing so my picture looks like this. This is my set C, and in here I have array alpha sub n, and in here somewhere is alpha sub n of 0. So I've just reparameterized it like that, and now I'm just going to utter the magic words. Geodesics are equicontinuous because they're Lipschitz 1. They're isometries, so they are way equicontinuous. It doesn't matter which of them you use. The Lipschitz constant is the same. And now we then say Arzela Ascoli. The alpha sub n, well, some subsequence, alpha sub n converges to L. This is a geodesic line uniformly on compact subsets. Okay. So we can pass to a subsequence of these so they converge to a line. It will be uniformly on compact subsets. It will be centered around here, right? That's where the convergence is taking place. Okay. Okay, so now J much bigger than I, much bigger than 0, I'm going to draw the picture. Here we have the line L. Now, here we have the line for the ray that diverges here, doesn't it? This is alpha J. And then we have the other picture, which is fine. So alpha J has gotten closer to L than alpha I does. And now we want that to be here. Here we want it to be, yeah, let's put it back here. This is so J is 0. This guy is alpha I of 0. Of course, this up here is L of 0. And we'll just remember who these guys are.
So they're always the same point, right? Alpha J of 0, alpha I of 0, it's always like 0 with your parameterization.
No, because I've reparameterized. So 0 is a weird place now. I've reparameterized so it's always in this C, but it's moving around in C alone. It's not a.
Oh, but it's just inside one.
Yeah, so I mean, to deal with the boundary, I usually choose a base point and choose rays from there, but these alphas are not going to be rays from the base point. Okay? They're just geodesic rays going from anywhere. Okay, so alpha of J0 is.
Oh no, but they are just in a fixed ball, that's all.
They are all in this fixed ball
Around x0.
around x0. Yeah, there's an x0 in here, but yeah, they're all in
That's
there.
why this stuff.
Okay, yeah, that's why we get the. Okay, so this is h sub I, if you remember, alpha of p sub I, and this guy is h sub j of alpha p sub j. Okay, now I take my G in question is going to be inverse of H sub G. So the product of those two elements in H. And now we just take this whole picture and we hit it with inverse, and we see the following picture. Now we'll do this in alpha. When we hit this with thing, it goes to here. Okay, and now I guess we'll keep that guy pink. He goes here. This is H, or this is G. And alpha. And then we have another picture. There we go. Okay, so now we start labeling points. Here we have P sub I. Here we have G of P sub J, just from, that's alpha P sub I. And over here we have and over here we have G squared with alpha P sub J. And here we have G squared with alpha P sub I. Okay. That's all right. Now what we're looking at is we're going to look at this guy. So I'm going to draw this guy here. And then I'm going to draw this guy here. Okay? Is everybody happy with the picture?
Sorry, is the yellow line down here the image of the yellow line upstairs?
No, the white line.
Different.
This goes to, yeah,
So
the
it's
color
like-
coordination is wrong. This should be white. Yeah, maybe I'll change that. Let's change that. Why not? Yeah, that's the white line upstairs. And the other white line isn't there at all. And now the yellow line down here is, well, not in the picture, but I just take this picture, I hit it once with G, or with thing to get it there, and then when I hit it with G again, it becomes this picture here, the pink and the orange. But the important thing to notice is that the distance here is very, very small. A lot less than 1, say, and similarly, the distance from the distance from here to here. And those distances are small, and this distance over here is going to be small as well. Okay. And now the point, will let theta be the angle on the blue thing there. So in the picture, he's right here. That's that angle. Okay, now, the point is, this is almost pi. Because look, I've got, well, it's exactly pi if you stay on the red through that, right? And I'm just moving, in the one hand, I'm moving from the red to the yellow over here, but these are just really close, so I'm moving a little tiny bit there, and just changing a bit there, and I'm moving a little tiny bit over here, and that's just changing a bit, and so there's no real change there from pi. Well, say G is not hyperbolic. Then, let's say the order of G is equal to n. Then we have these guys, G sub k of alpha pi. These are the vertices of an n-norm in our hyperbolic space, right? Because it's just an orbit of a point under a finite order element. Okay. And the interior angles are all theta, right? You just hit that thing with G and it gives you all of the interior angles of that polygon. And the point is, the angle sum of an n-gon in X is less than or equal to the angle sum of an n-gon in Euclidean space. You just use, well, you slice off a triangle and argue by induction, basically, right? Slice off the triangle we already know this is true for, and so by induction we're done. Okay, so, but we know what that is, right? That's, didn't even have to look this up, I was so proud of it. That's n minus 2 times pi. Okay? But this thing is almost pi. Right? So this says n theta is less than or equal to n minus 2 times pi. And solving that, I get 2 pi over pi minus theta less than or equal to n. And of course, n goes to infinity as theta goes to pi. So that's the proof. Okay, now we get sort of the obvious corollary. Every cat zero group has a hyperbolic element. because if you take a group that acts properly discontinuously and co-compactly on a cat zero space, every point in the boundary is a conical limit point because there's a n for which the translates of an n ball cover. Yeah, that's clear then. Oh, there's, well, we need another, yeah, that's not quite clear yet, is it? Finite subgroup fixes a point. Every finite subgroup will fix a point in the cat zero space, and therefore there is a uniform bound on the size of a finite subgroup using properness and co-compactness. Right? So in claims fairly straightforward. Oh, yeah.
Because in general, your argument didn't give a hyperbolic element.
No, it doesn't give a hyperbolic element, and it doesn't give you any control on where the axis of that hyperbolic element would be. You would think it would, but it doesn't. In the presence of flats, you can be, this whole argument can take place a long ways away from where the axis of the hyperbolic element is.
Discreteness is not sufficient. And properness of the action is not sufficient. You have examples where
Yeah.
you have arbitrarily high orders.
No, it's the corollary if H is an infinite subgroup. This is cat zero group. Then H has no conical limit points. Okay. So now this is a little strange because every non-elementary Kleinian group has a conical limit point. So somehow weakening of negative curvature leads to rather bizarre results. We're almost out of time, so I'm probably just going to skip ahead to what else is known.
Can this be generalized to H not being the subgroup, but just the group acting properly discontinuously and some extra condition?
Well, this?
Yeah.
I don't think so.
So
I
you
don't see
absolutely
why.
have to have a group acting properly.
Yeah, because otherwise, yeah, without the I mean, you just get the original result, right? There's no bound on the order. So if there's an infinite torsion subgroup with a conical limit point, then there's no bound on the order of the torsion elements in it, right? So
So in
it's
the hypothesis and get this.
somehow, yeah. Anyway. I'm just going to state these theorems because we're about out of time. G is acting on X geometrically if the diameter in the Tits metric of lambda H is greater than 2 pi, then H contains a hyperbolic isometry. Okay, so if the diameter of the limit set is more than 2 pi, this is just a pi convergence argument, basically. Contains a hyperbolic isometry, and the other thing I know tripling and a subgroup of G infinite torsion, if the dimension of the boundary is minimal among such, so if it's the minimum dimensional counterexample, then limit set of H is infinite. The radius in the Tits metric of the limit set of H is greater than, I think it's greater than or equal, greater than strictly, but it's at least greater than or equal to pi halves. And H doesn't fix a boundary point.
Is the diameter like half the diameter?
No, the diameter is the, the radius, this is the extrinsic radius. So you consider all points in the Tits boundary, and you look at all the balls that contain the limit set, and you take the infimum of all of those.
Doesn't the second imply the first? Because if the radius would be smaller, then it would fix.
Yeah, no, there's implications here. I just wanted to, these are not unrelated. They're all kind of the same thing. This and this are certainly not unrelated. Certainly this were finite, then it would immediately fix a point, well, virtually. I should say virtually. That's really what I mean, but yeah. Okay, so that's, as far as I'm aware, that's all that's known about this. There has never really been any study in this setting about what kind of limit points you can have in a cat zero setting. There doesn't seem to be any results there at all. Everything that's known is pretty much coming from the classical setting. Negative curvature, pinched negative curvature, I guess, is the farthest that it's been taken, and that was by Bowditch a long time ago. Anyway, I'll let you go now.
So, in the cube complex case, what is the extra information that Wise and Sageev are able to exploit?
Okay, how are they able to? Okay, so in the cube complex case, right, the whole idea of a cube complex is if you look at a hyperplane stabilizer, it is a codimension 1 subgroup, right, provided the hyperplane separates deeply on both sides, right? So, so the proof of Wise and Sageev proceeds by induction, right? They're doing the Tits alternative for a group acting on a cat zero cube complex, right? So you take, you know it's true in dimension 1, right? Because then you have a tree, right? And so you assume it's true for the dimension below you, and you take a hyperplane and its stabilizer, right? So you're in the dimension below. It is either has a free subgroup or it's virtually abelian, right? So if it has a free subgroup, you're already done. And if it doesn't, well, I mean, the Wise and Sageev method is if it doesn't, you just hit it with the algebraic torus theorem and take care of it that way, right? You have a group that has a codimension 1 virtually polycyclic subgroup. Therefore, it's either virtually polycyclic, in this case, virtually abelian because it's cat 0, or you get a splitting over some virtually polycyclic subgroup. And now with that splitting, it's easy to find free groups, right? You have a splitting, right? So free groups are sort of inherent in any splitting. So that's how it works there. So, yeah, I mean, that's how the Tits alternative works.
I was actually reading that paper on the way in.
Ah!
Deliberately, because this all can they can also do it just with proper action on a cat 0 cube complex, but they need a bound on the orders of its finite subgroups. So they can take it further, but with that additional hypothesis.
Okay. So you came prepared. Dang, I didn't.
I've been meaning to read it for a while,
Yeah,
so it seemed like the right.
That makes the theorem sound quite quick, actually. I feel like I've...
It's only 7 or 8 pages.
Oh.
It isn't that big, is it? I didn't think it was that big. You got it.
4 pages if you don't include the references.
Yeah, okay, yeah, it is not a long theorem.
On a le Coulomb-Girardet example.
What?
The Coulomb.
I have no idea about their example.
Ah.
I don't know, other people may, someone else may have done their homework, but I just am aware that this example exists. Okay, I have not read through it.
I mean, it's pretty... It's the one I'm thinking of. It's a pretty involved construction. Rework quite a lot of wider stuff.
Yeah.
So it's a proper space with unbounded dimension.
No, I don't think the space is proper.
It's not proper.
Yeah.
Yeah, I don't think the space is proper, at least that's what I understand.
So somehow they need to do, you want to do small cancellation theory to build a torsion group, but they want to do cubical small cancellation theory to build it. So it involved
Yeah.
both of those.
Yeah.
Making those two pieces of machinery work.
Yeah, no,
That's
that
like
it
what I
seemed
would
right.
promise.